I'd like to redo a few of the problems that I did with you in class the other day. I'm not completely happy with the presentation that I made, and I want to just be sure that you really have it. And this is one of the problems, one of the first ones I did with you here. You'll notice in this case I've got a cost function, which again gives you the total cost function. Any point on this function would have the coordinates q and c of q. Again, q is like the independent or the x variable under normal circumstances that you'd be plugging into the dependent function c. So this is again your x and y coordinates, or your independent and dependent. So your coordinates of this point would again simply be q and c of q. Now remember how we calculated an average function? The average was equal to the total divided by the number of items. And simply speaking, that's just c of q divided by q. If I subtract 0 from the top and bottom, I've literally done nothing. But what I have now, frankly, is a simple version of slope, where if I think of this as my coordinates q and c of q, and the origin, of course, would be 0, 0, then to find the slope between these two points, the slope of that line, I would simply take the difference of the y's over the difference of the x's. So in other words, your average cost function could be thought of as a slope. And you'll notice that in this case I have a slope of about 1. And of course, if we want the smallest possible slope, you would want this number to be as low as you possibly could. So what you are really after, if you want the lowest possible slope, and therefore the lowest possible average cost on this function, what you're looking for is the first place that that tangent line through the origin would touch your cost curve. If I were to go up higher than this, if I were to raise that number, you see it would actually increase, it would hit more than one place. These would be higher. You want the lowest possible value, so you want the first place where the tangent line drawn from the origin touches your cost curve. So graphically speaking, this point would be where your lowest average cost would occur on your cost function. Let's move on now to number 5. In this case, I have a given cost function of c of q equals 5,000 plus 36q. I want to find the following. First, I want to find the cost of producing 500 items. You'll notice that c of 100, plugging 100 directly into the cost function, gives me 5,000 plus 36 times 100. That gives me a total of 8,600. So the total cost of producing 100 items would be $8,600. If I want the cost of simply producing the 100th item, all I need to do is take the marginal cost, which is the first derivative of the cost function. The first derivative of this cost function is a constant, 36. That makes sense because you'll notice that this was a linear function. The cost per item was a constant. It was $36 per item no matter what. So the 100th item, as well as any item on this function, would be $36. If I want the average cost of producing 100 items, I want you to notice that there's two ways to look at it. First of all, I want you to think of it like it's simple arithmetic. The average of 7, 8, and 9 would simply be the total of 7, 8, and 9, which is 24, divided by 3, which would be 8. In this case, if I simply want the total divided by the number of items, I will take my total, which you'll recall was 8,600, and there were 100 items. So if I want the average cost per item, I take the total of cost of all items, divide by the number of items, and that gives me the average cost per item, or $86. But let's talk about a more general case. That's really what I'm more interested in here. Again, the average cost is equal to the total cost, or c of q, divided by q. In this specific example, it'll work this way. Remember, our cost function was 5,000 plus 36q, and q does not change. So if I want the average cost, I just take the cost function and divide by Q. In this case, I'm going to separate my one fraction into two. I'll think of this as 5,000 over Q plus 36Q over Q. On this fraction, of course, my Q's simply cancel and I have 36. I'm going to take this Q, bring it up to the top where it will be Q minus 1. So in this case, my average cost function would be 5,000 times Q to the negative 1 plus 36. I now have a function where I could find the average cost by merely substituting the value. In this case, let's go ahead and substitute our 100. We'll find the average cost of 100 items. Substituting in, I have 5,000 times my Q to the negative 1 power plus 36. And here off to the side, I've done the calculations for you. And not surprisingly, once again, it works out to be $86. The key to the average cost function, the thing I most wanted you to see, was you simply take the total cost function and divide by the number of items, which is Q.